Hello, hello Lucia. Welcome to the stream. Welcome back. Thank you. Is everything working properly from your side? All good? Great. Because I changed a few things of my setup. So just want to make sure. Anyway, so today we're going to be solving the bi-weekly contest from last week, 136. So I see the chat messages don't appear as banners in your screen share anymore. Yes, I'll probably have to set that up. Well, thank you for the feedback. I'll look into it afterwards. Anyway, so let's get started. So here's the link to the contest. Why can't I paste? Okay, I cannot paste the link. I don't know what's going on in chat. Anyway, so let's start. Never mind, I can look it up. All right. So let's start with question 1. We have 4 questions as usual, and we have a 2-part question. Q2 and Q3 are part 1 and part 2. So we gotta... Oh, that's the link. Thank you. So we gotta check that out if they are either... Whenever you have a 2-part question, you have to make sure, you have to check if they are actually the same question but with different constraints, or if they have a significant difference. Because if they are the same question, then you can solve the harder one only and then reuse your solution, and in that way you can save time. Anyway, so let's go to question number 1. Find the number of winning players. You're given an integer and represented the number of players in a game and a 2D array pick, where pick of I is x of I and y of I, represents that the player x of y picked a ball of color y of I. Player I wins the game if they pick straightly more than I balls of the same colors. Okay, so it depends. The number of balls that they have to pick depends on the number of the player. So yes, it has to, for player 0, it has to be greater than 0. But this is it's called a game, but seems pretty independent, right? Each player pick up balls. I guess they don't tell you if there's some competition, if they're competing to pick up the same balls. You just get the information of how many balls each one pick. So yeah, because multiple players can win the game. That's pretty obvious. Okay, so n is only up to 10, which is the number of players. And then the number of pickup of balls pickup is up to 100. So as usual with an easy problem, the those constraints are pretty small, so we can just do some brute force. So we can go over each player, right? And then we want to count how many out of the peak, if the player is equal to our current player, then we want to count this color, right? The color of the ball. And we want to know if there's any in the counts. So if we go over the values of the counter, so how many times each color occurred, if this is greater than P, so for values in counter, okay, so, and we want to sum that up. So bear with me. Okay, so we didn't close some parentheses, I guess here. Yeah, sounds good. Okay, so we go over the players, and then we count the colors that have for that player. Then we go over the values to see how many times each color occurred. And if in any case, oh, it's the other way around, right? If the balls, yeah, that's the other way around. We could use mean over the counter values too, I guess. I think you mean max. No, just one. Yeah, it's max. The reason I don't use max is that, I mean, yes, you could, but there's a special case where there is none for that player, and you would need some default for that case. But here it's going to give us false, so it's going to add 0 in that case. So that's why I prefer the any. Also, another benefit is that with the any you can stop early. Like if you find any example that is greater, you just stop going over the values. But with the max, you must go over all of them. So that's another, I mean, it's a minor, it doesn't make a big difference, but it's just something to take into account. Okay, so this solves the problem. And it's pretty fast, but notice that this is not, so what is the order of complexity here? It's n, O of n. I mean, we go over all the players, but then we go over all the peaks, which is 100, right? And then we go over the values of those. But so we are multiplying the number of players times the number of things that we pick. So we're going over this list for every player, right? And we could save that do it more efficiently by just going over the list once. And so we would have the counts, and we have a default dictionary that is going to count for each player. So we do this, and so now what do we do? Now we only, okay, so let's delete this. So we go over each player. We don't care what the number of the player is, so we just want the values, right? And the values, yeah, the values are gonna be a counter, right? So this is a counter, and we want to go also over the values of the counter. And here we check our any. Oh, we do need the, I forgot, we do need the player, because that determines how many points we need. So if any is greater than the player number, then we add it. And I think that should be it. So I don't expect this to be faster, because the numbers are so small that it doesn't matter. But notice that here the order is not the product of the players. They're not multiplied, I think. Okay, so let's move on to question 2. I'm gonna, when I export the video into YouTube, I always add all the links in the description to the problems and my solutions, so check that out. So I'm having trouble sharing the links right now, so I'm gonna do it. Notice that if you find the YouTube video, you can go over all the solutions if you're interested. So okay, so minimum number of flips to make binary grid palindromic. Okay, so I told you that you want to check if they are the same problem. It turns out that it is not. So in some contests, they give you, in some contests, they tell you, okay, so this question is the same as this other question except for this and this. But LeetCode doesn't do that. I would prefer if they did it, because otherwise you have to start like comparing. So notice that this part is different here, so it seems like it is not the same problem. So we're gonna solve them separately. Okay, so here we have a m times n binary matrix, and binary matrix grid. Okay, so is it a grid or is it a matrix? Okay, so a row or a column is considered palindromic. Okay, we know what palindromic means. It's the same forward and backwards. So you can flip any number of cells, which means the flip you change 0 to 1 or 1 to 0. So we have to return the minimum number of cells that need to be flipped to make, and here we have to pay attention, either all rows palindromic or all columns palindromic. Okay, so this is, so we can try, so there are two options, right? They are either all rows or all columns. So we can try both, right? We can try both. And this pretty much decomposes into a problem where we want to know the cost of making palindromic just some list in one dimension, right? So we could have that. We could have a mean cost or mean flip, let's call it mean flips, of some array. And so this is pretty simple problem, right? So you go over half of the position, so each position is going to have a pair, right? Except for the middle one if the number of elements is odd, but each of the others are going to have a twin, so-called, and if they are the same, I have an idea. All right. Let's hear it. But what I was saying is that they are so each pair is independent, right? We have to make them equal. So if they are the same, we don't have to do anything. We don't have to do any flip. But if they are different, we have to do one flip. Add these tables. And then set them to the sum, to be the sum. I'm not following your idea. Sorry. So here, if a of I is different than a minus 1 minus I, this is the pair, then we add a 1, right? Because we have to change. To make a change there, we have to make a flip, right? So one if they are different, one is going to be 0, the other one is going to be 1, and we could choose to flip any of them, right? It doesn't matter. And notice that if you could, so if this was not binary and you had to change, this would work as well, right? If you could change any value to any other value, this would also work, because only when they are different you have to make one change. And so here, so we can use a trick, because as we said, we have to try with the rows, and then we have to try with the columns. And so what we can do is to just we're gonna do a transpose. We're gonna flip the matrix so that the rows become the columns and vice versa. So we're gonna do this twice, right? And so we go over, so yeah, let's say I usually like to have the sizes. And so here we go over the rows, and we sum the mean flips for each of the rows, right? And this is our current cost. This is our cost for all the current rows, and so we want the minimum, right? So we update our minimum, but now we want to flip the matrix so that if we do this again with the rows, now the rows are going to be the columns, right? And how do we do that? We just do this. So we swap first the sizes, and then we also want to swap. So we want to go over each column first, and then over each row, and we just do this. And that's going to be the flip of the grid. And that's it. So it takes 2 seconds and a half. Well, I guess the flip is not so if you kind of duplicate the code, it might be a little faster, but we don't want to do that. We want to avoid duplication so that our code is shorter. All right, so let's move on. Oh, that's cool, nice. Thank you. So let's move on to part 2, question 3. So this is the same. The only thing that's different. Thank you for the link. The only thing that's different is that here, yeah, and be careful with this, because during the contest I made the mistake of thinking that this was, I thought the problem was the same, and the only thing that changed was this, that the total number of ones was divisible by 4. Well, I made many mistakes, but you should, there's another difference that is not highlighted here, which is that all rows and all columns have to be palindromic. In the previous problem, it was an or, but here is an and, right? And that makes a big difference, right? That makes a big difference. So make sure you read the problem carefully, and make sure you don't assume that if they are 2-part problems, that they are the same. It's a little tricky. That's why I would prefer them to tell you exactly what the difference is. Okay, so how do we solve this? So this is more complicated, right? Because we cannot just solve every one-dimensional array separately, right? Because, okay, but let's investigate a little bit. So let's say that we have a matrix of size 5. Right, so we have something like this. And so notice, so let's consider the first cell, right? So this cell here. So this cell has to be the same as this cell, right? Because this row has to be palindromic. But also this cell has to be the same as this cell, right? Because the column also has to be palindromic. And by the same idea, this row has to be palindromic, so this has to be the same as this. And this has to be the same as this, so all these 4 values have to be the same, right? And the same is going to, so this value has to be the same as this one. Well, maybe the colors are kind of can be confusing because they had to be the same between these 4 values, but not between the others, between the different groups of 4, right? So this 4 have to have the same value, and okay, and the same is going to be, it's clear, makes sense, and the same is going to be true for these values here. We can partition all these cells into groups of 4 that have to be equal, right? But here, so for example, the one in the middle doesn't have to be equal to anything. It doesn't have a pair, right? So this one is special. It's a group of only 1. It could be a 0 or a 1, it doesn't matter, right? And this one, so this one here has to be the same as this one. This one here has to be the same as this one. This one here has to be the same as this one. And this one here has to be the same as this one. So in this case, we partition them into groups of 2, right? So one way, so the ones that are colored like this are groups of 2. The ones that are colored in blue are groups of 4. And the ones that are colored in red are groups of 1. Right? And well, notice that this is the case because this matrix is odd, is 5 by 5, so both of the dimensions are odd. But if you had a matrix of size, I don't know, 4 by 3, for example, so 4 and 3, then you would have you wouldn't have a red one, right? It would be like this, right? And if you had only like a 2 by 2, then you would only have blue cells, right? Because they are only groups of 4, right? Only when you have odd sizes is when you have cells that are in the middle. All right, so let's handle each type of cell separately. So let's start, well, let's start with the red one. The red one is easy, right? Because we have to make the number of ones a multiple of 4, right? So if we have a 1 in the red cell, then notice that the parity of the number of ones in the end is going to be odd, right? Because all the others come in multiples of 2. They are either pairs or they are groups of 4, right? So, and they all have to be equal. So if you have a 1 in the middle, then the number of ones is going to be odd. So that means that if we have a 1 in the middle, we have to change it to a 0. So here, if we have a 1, we have to change it to a 0, and the cost is going to be 1, right? 1 flip. And that's independent of what we do with the other cells, right? So we can handle that separately. And we only have, remember that we only have a red cell if there are if both dimensions are odd. Okay, so now let's handle the case of size 4, right? So notice that the size 4 groups, they're all have to be 1s or they all have to be 0s. And so notice that they don't matter for the number of ones when we have to make the number of ones equal a multiple of 4. It doesn't matter whether we have 4 zeros or 4 ones. They won't change the remainder when divided by 4, right? If you add 4 ones, it doesn't change the remainder. So we can ignore the 4s when we are handling this multiple of 4 condition, right? The only thing that we care about, if we have to make them all the same, so we have 2 options. We make them all 0 or all 1, and we choose the one that has the least cost. And each of the groups of 4 are independent, and so on. And so this is pretty simple. The harder case is the case of 2, right? Because that's going to that's going to matter when we want to make the number of ones a multiple of 4, right? So just join in the middle of this. I'm so lost. How do you know how you want to split the grid? So this is just an observation. It's not, we're not, so we're asked to make all the rows and all the columns palindromic. So what I said is that if we consider the cell here in the corner, so for this row to be a palindrome, these 2 have to be equal. And for the first column to be palindromic, these 2 have to be equal. And now these 2 have to be equal, and these 2 have to be equal. So we have a group of 4 cells that all of them have to be equal. And the same happens with all of the blue cells. They come in groups of 4. But then the one in the middle, the red one, is different. It doesn't have to be equal to any other cell, so that's why I I paint it in a different color, and then the black ones are the ones that come in pairs, right? And so now what I said is that for the red one, I'm deciding how to make the changes to satisfy the condition that it has to be a multiple of 4. And so the one in the middle, the red one, doesn't have, in order to make it a palindrome, the rows being the rows and columns, the red one doesn't matter, but it does matter when we want to make the number of ones a multiple of 4. And that means that it must be a 0, because otherwise the number of ones is going to be odd, because all the other cells come in pairs. They won't change they will make the parity 0. So that means that if we have a middle one that is a 1, we have to flip it to make it 0. Then the ones that come in groups of 4, we have two options. We make them all 0, or we make them all 1. We choose the one that has the minimum cost. And they don't matter in terms of the remainder when divided by 4 of the number of ones, because they either add 4 or they either add 0. And so they don't change the remainder when divided by 4. And now the hard case is when we have the ones that come in pairs, right? So, and we're gonna think about them. There are 3 types, right? There are 3 types of these pairs. There are the ones that are 0, 0, the ones that are 1, 1, and the ones that are 0 and 1, right? In any order, it doesn't matter. So we have 3 cases. So let's say that we count how many we have of the 1, 1, right? If this number is even, then we are done, right? Because we have an even number of pairs. That means that the ones are multiples of, the number of ones are multiples of 4. The ones that are 0, 0, we don't have to change, right? And they won't add anything to the number of ones. And these ones, we have to make one flip, and we're going to choose to flip the 1 to a 0 so that it doesn't change the number of ones. So if this is the case, we are done. And the other case is that the number of 1, 1 is odd, right? And so if the number of 1, 1 is odd, it means that it has a remainder of 2 when divided by 4. So now we have 2 cases, right? We have, if the case of 0, 1, if we have if the number of these ones is greater than 0, then we can change the 0 into a 1, and that's going to make the remainder, where it's going to add 2 1s to the total number of ones, and that's going to make it a multiple of 4, right? And we're getting that for free in a sense, because we already know that we have to pay 1 flip for each of this kind. For the pairs that are different, we have to always pay 1 flip. But now, if we're in this case, we care about which number we flip. We flip the 0 to a 1. That adds 2 to the number of ones, and that makes it a multiple of 4. And the other case is that the 0, 1, the number of 0, 1 is 0. And in that case, we are forced to change one of the 1, 1, change a pair of 1, 1 into a pair of 0, 0 with cost of 2. So in that case, we have to add an additional cost of 2. Or a pair of 0, 0 into 1, 1. Yes, that is correct. The thing, there's a catch, right? Because you know that you must have a 1, 1, because, yeah, that's my point. There's always a 1, 1, but not always a 0, 0. Because given that the number is odd, the number of 1, 1s is odd, you know that there must be at least one, right? Okay, so that is the idea. How do we implement? So the code is not so bad once you have the whole algorithm. So let's so we have the red case, which, like we said, it only happens so if both have parity 1 and grid, the one in the middle is going to be this. It's a 1, then we must change it, right? So we add 1 flip to the result. And now let's deal with the ones, the blue ones in my diagram. So we go over this. Notice that you can go over this square, like the upper left square, and then you're gonna, each of those is going to represent a group of 4 in the other squares, right? So here, and this division by 2, since it rounds down, it's going to leave the potential middle row and column excluded here. So here we want to sum. So we have a row. The row has to be either, so it's either R or R minus 1 minus C. And the column is going to be either C or either C minus 1 minus C, right? So these are our 4, and we want to add the value there, and our cost is going to be the minimum between cur. So cur is going to be the sum of 1s, right? So we either flip all the 1s into 0s, which is going to have a cost of cur, or we flip all the 0s into 1s, right? Which is this. I guess we could call this O of 1s. And so we choose the 1, and remember that this doesn't matter for, and now we want to go over all the pairs, right? So we have to go over all the pairs. So one trick, we could use the same trick that we used in the previous problem. This trick. So to handle them, to handle just the rows, and so we wanna check the middle row if there is one, and that means that only happens if the number of rows is odd, and in that case we want to go over the columns here. And what do we want to do? We want to, so remember that the condition is going to be how many pairs, 1 pairs there are. We want to know the parity of that, and also we want to count exists 0, 1. So cool generator for loop. Oh. Okay, so here we have the elements, the middle row and C, and we want to compare it with the middle row and C minus 1 minus C. Okay, so we care about the cases where they are both 1 because we want to count it, or we care about the case in which they are different, in which case exists 0, 1 is going to be true. And here remember that we only care about the parity, so we can even do this. And so now we have our cases. So remember, we only have to add 2 more. Oh, so no, here we also have to, since they are different, we have to we're forced to change 1, of course. And so here we only have to, if the pairs of 1, 1, the parity is 1, so it's odd, and we don't have a 0, 1 which we can use for free, then we have to add 2 to the result. And so that should be it. Don't understand. Yeah, that's true that we can do a flip. Yeah. Yeah, this is just doing a transpose. So in our code we only care about the yes, I'm flipping the grid. So that I'm only dealing with the rows, with the middle row, and when I flip it, now the middle column is going to be the middle row. Yeah, I don't know if you say so. You're the cock master. I find this easier to explain. Anyways, so yeah, so I think I really like this problem because it doesn't require any previous knowledge. It's just reasoning from first principles. And yes, and you need to have an explanation. So yes, it's kind of case analysis, but you have to do it in a clever way so that you don't have too many cases. So I really like this one. Even though it cost me a lot. So in this contest, I got 268th place. I think this is in the merged rank. But this is because I misunderstood. I misread, like I said, I misread the Q3. And so I coded a solution that was solving a different problem. And so it took me a longer time. I had to start over, like after 1 hour in the contest. I had to start over. Happens, yeah. Okay, so let's move on to question 4. Time taken to mark all nodes. There exists an undirected tree with n nodes numbered. Oh, thanks for the link. Number 0 to n minus 1. You are given a 2D. Okay, so we get an undirected tree as in the usual way, and all nodes are unmarked. If I is odd, the nodes will get marked at time x if there is at least one node adjacent to it which was marked at time x minus 1. If I is even, the node that will get marked at time x if there is at least one node adjacent to it which was marked at time x minus 2. To this one, your solution to this one? Oh, worked a lot to make it pass. No, I haven't seen it. So I didn't have any problems to make it my solution pass within the time limit. So this is a little hard to understand, to even understand this explanation. So return an array times, where times is when all the nodes get marked if you mark node I at time t0. So I think another way of looking at this is, yeah, I guess the expected O of n, but my solution was n log n. That's interesting. Yes, my solution is O of n. So we have a tree, and we have to, so what we're told is that if the node, so the nodes have numbers, and so if you move from node 0 to node 1, then it takes, depending on the value in the node that you move into, it takes you 1 time, 1 unit of time, or 2 units of time. That's what it means. That's why I say it's hard to understand. So yes, if it's even, it takes 2 units of time. The idea of rerouting. Okay, I'm gonna explain it. That's what I did. I did the rerouting, and I'm gonna explain it so maybe it will be easier to understand. So here we can think of, instead of thinking about the nodes, we can think about the edges. So if we go from 0 to 2, we can think about this as a directed edge, and this is going to have a weight of 2 because the node that it goes to is even, right? And this edge here is going to have a cost of 1, and this is going to have a cost of 1, and then if we have a 4 here, this is going to have a cost of 2. So this boils down to finding the farthest, the longest path starting from each node with this weights, with these weights that we just defined. So this is what it's called, the all longest paths in a tree, and this is a very well-known problem, and the way we can solve it is we can root, for simplicity, let's root the tree. This is not a rooted tree, but we can choose any node as the root. Let's say 0 is the root. And notice that if we find the if we try to find the longest path from a node in its subtrees, then in that case we can do it recursively. Hi, Spam. The idea is to calculate this for all roots. No. So there are 2 different ways. There are 2 different things. One is what the algorithm that I'm trying to explain, where I'm saying let's choose. Hey, thanks for the follow, Spam. I don't have the notifications. I have to fix that. So the idea is to calculate this for all possible roots. No, we just choose any node as the arbitrary root. So 0 is the one that I chosen. And so what I said about the here what it means is that if you move into but at the end of the day, basically we want to compute what the value would have been if any node would have been the root, right? The root is just a convenience. We're not going to we're trying to compute the longest path from all nodes. When it says all longest paths, it means that we're gonna start from every node. And what I'm saying is that if you do this recursively, right? So here we have node u. Semantics, like yeah, I guess you could call it that way, but I'm not rooting the tree. So I'm saying I'm calculating the longest path starting from each node, but that doesn't mean that it is a root. I guess you could call it that. Okay, so here, if we do this recursively, it is easy, right? So we find the longest path in the subtree, in all the subtrees, in all the children of u, and then we get the maximum and we add 1, and that's going to be the longest starting from u, right? So but this only considers the paths that go down the tree. But what happens if we have so we can classify all the paths depending on whether they move down or they start moving up, right? So if we go from u to its parent, let's call it p, right? So this could be the longest path could go this way, right? And then we want to find we have a recursion, right? We want to find the longest path starting from p. But what is the problem? The problem is that when we are trying to solve the problem of finding the longest path that starts at p, it could be that the path goes down again, and in that case we're repeating an edge, and that's not what we want. So the idea is to detect when we are in this case where we're going to u to p and then from p to u again, and in that case we want to go into the second longest path, right? If going from p to u gives you the longest path that goes down, we want to consider the longest path, the second longest path that goes down. All right? And so that is the key idea. Maybe when I write the code it's going to be clearer. So okay, so we first construct the adjacency list of the tree. So we go over the edges, and just for simplicity, let's say I'm gonna write down this function that gives us the weight of an edge in the way that we defined it. So remember that it depends only on the parity of the node that we're going. So this is the parity, and if it is even, so the parity is 0, then it's going to be 2. But if it is 1, the parity is 1, it's going to be 1, right? So that's the formula that's going to give us our weight. And so we're going to compute. We're going to do 2 DFS. The first DFS, we're going to just do the recursion that we mentioned, but we're going to find the distance, the longest distance of paths that go down.
right? So here we're going to call this DFS1. So we start from node 0. Initially, the parent is -1. So this is standard code for. So if B is different than the parent, then we call recursively, right? And now we want to compute. So we have a path down that goes from, we have the edge that goes from U to B, and then we have the best down path that starts at B, right? Our children, our current children. And so we want to know if the current is better than our best path, our longest path. If it is the best path, this is standard code for getting two maximums, right? So here we have to update both our maximums. So the new value is our new maximum, and the old maximum is now our second maximum. And otherwise, if cur is greater than the second maximum, in that case we only update the second maximum, right? So this is going to give us this is going to calculate this right here. So let's call it. And now we want to calculate the best path that starts going up, that starts going to the parent first. So we're going to do that with DFS2. And this is going to be similar in this case. So this is the same thing, but now we want to know if, like I said, if we move up and the best down path from my parent. So here I'm gonna calculate the app of B, right? So we want to calculate the longest path that first go up starting from B, and U is our parent. So I want to consider going up from U, right? And I'm gonna have to consider the weight from going up, right, from B to U. But the other option is going down from U, right? But I want to see if going down from U hey Bima, hello. Going down from U is equal to going down from B plus the weight of U and B. Because if that's the case, then I have to go down to the second longest path. And here I have, otherwise I use the longest path going down, not the second one. And that's it. And now we call recursively. And so we call this here. And so now finally what we want, in order to get the longest path for each U, we just get the maximum between the longest path down and the longest path up. U. So this should be it. And it works. So at the end of the first DFS, are the down values of every node valid, or is 0? The only valid down value. They are all valids. I don't know if I understand your question. So we initialize everything with zeros, which means that, so it could be that there are no two paths. So if a node has only one child, then there won't be a second path. And in that case, the second down path is going to be 0, which is what we want. Aren't dn1 and dn2 actually the longest paths starting from that node after the first? I mean, we're only changing, we're not changing, so dn1 and dn2 are changed only by dfs1. Yes, they are the, so dn1 is the longest path. Yes, for leaf it's going to be 0. Yes, because here we want for a leaf, this is not gonna enter this part of the code, and so it's gonna leave the 0. But yeah, notice that in the second DFS we don't modify dn1 and dn2. We just set the app longest path. How do we know if we loop back? The logic for app. So the logic for app is so here I call them, maybe I should use the same names. So I'm considering B. I want to move app from B to its parent, right? So I want to go up from B to its parent, and then I want to find the longest paths from U that could move up or could move down, right? I don't care. I only care that the first edge goes up, right? But what is the problem? The problem is that if I consider a path that goes down, the best path that goes down, it could be that it goes down into B, and in that case I'm gonna have an invalid path, right? So if the path with B is the longest one, then if I use the second longest one, let's say this is B prime, this is another child of U, then I would have to choose that. So that's why I have here I have this condition. This condition is checking if the longest down path from U is equal to the longest down path from B plus the edge that goes from U to B, right? So that's the case where we're gonna move up and then we're gonna move down into the same node into B again, and so in that case we use the second longest down path. Otherwise we use the first longest down path, and we consider both. We consider the up path, the up path from U, and we consider that the down path from U, right? And we add the edge that goes from B to U, which is the first edge that goes up, right? Because we're computing up of B. So that, yeah, I mean, it's not easy to wrap your head around it, but I think with this diagram, it's not that hard. So I recommend, so it's disappeared. Can you look at my submission? I can look at it after the stream. I have to finish the stream in a moment. I think there's a thread where you share your solution. Maybe I can look it up there. But yeah, this is the runtime is 3.2 seconds. So it's pretty far from the limit, and it seems to be efficient, relatively efficient. So this idea, this rerouting idea, or the all longest paths, came up recently in LeetCode. So you could have, I think it's useful to have a template. Yes, it's weird. Yeah, n log n. Yeah, usually a logarithmic factor doesn't make much difference. But yeah. Anyway, so I think that's all. I'll have to look into the setup of the stream in order to get back the notifications that I had for followers and for and displaying the chat. Oh yeah, that's going to be a problem in the YouTube video, right? Because how did people did it in 900? Seems like similar. I mean, they do have 2 DFSs. Oh, they hack it. This is... Are they hacking? Seems like they are changing the time. They are changing the time of that's your that's your answer. What the hell? Yeah. Well, this one doesn't have any hacks, I think. But they are doing 2 DFSs. I don't know why it's faster. Anyways, that's all I got for now. Thank you guys for your support, and see you in the next one. Bye bye.